So now we are going to talk about a rank of matrix and its significance in vector spaces. So our objective, understand the concept of matrix rank and its relationship to vector spaces. Next, we have learned how to compute the rank of matrix using row reduction and understand the implications of matrix rank for the row space, column space, and null space of the matrix. And we're going to apply rank in the context of solving linear systems, sorry, and the rank nullity theorem. So first, let us define matrix ranks. So the dimension of the row space or column space of a matrix. So that is a matrix rank. Next, we're going to know the key properties of rank. We have row rank. So this is the column rank or the rank theorem. Next, the rank is the number of linearly independent rows or columns. And the rank tells us the linear dependence of rows slash or columns. And what is a geometrical interpretation? So this is the rank represents the number of independent vectors that span the row or column space. Next, let us define row space and column space. So the row space, the subspace of R raised to n, spanned by the rows of the matrix, and the column space is the subspace of R raised to m, and that's spanned by the columns of the matrix. And the key relationship of both, or the rank of the matrix, is the dimension of both row space and column space, of course. And so now let's proceed to row reduction and computing rank. The row reduction method or the Gaussian elimination. We're going to use the row echelon form or the REF to count the number of non-zero rows. So we have two basic steps here. Perform row operations to reduce the matrix to REF and count the number of non-zero rows. This gives the rank. So for example, we're going to walk through an example of row reduction and determine the rank. So let us consider the matrix A is equal to 1, 2, 3, 2, 4, 5, and 4, 5, 6. So the step 1, we're going to start with the original matrix, which is this one. And step 2, subtract 2, 2 times the row 1 from row 2. So 2 times the row 1, so we have row 1 is 1, 2, 3, right? And if we're going to times 2 to it, so 2 times 2, 2 times 1 is 2, minus 2 in the row 2, the first one, which gives us 0. Next we have 2 times 2 is equal to 4, minus 4, that is 0, and 2 times 3, that is 6, and minus 5, so the answer is negative 1. So now our row 2 is 0, 0, negative 1. So next, we are going to the step 3. We are going to subtract 4 times row 1 from row 3. So this time, our answer we are going to write on row 3. So 4 times 1, that is 4, minus 4, which gives us 0. 4 times 2, that is 8, times 2, 4 times, I got lost. Okay, so 4 times 2, that is 8, minus 5, so that is negative 3. And 4 times 3, that is 12, minus 6, so the answer would be negative 6. So we have in our row 3 now, 0, negative 3, and a negative 6. And our last step, we have step 4. We're going to add 3 times row 2 to row 1. Okay, so that we were going to come up all zeros below. And now this is a row echelon form of REFs. The rank of the matrix is the number of non-zero rows, so which is 2. So the rank of the matrix of A is 2. So next, we are going to rank and solvability of a linear system. So the relations to consistency of linear systems. A linear system AX is equal to B is consistent if and only if the rank of the augmented matrix AB is the same as the rank of A. So we're going to discuss conditions for unique or infinite solutions based on rank. So example, we're going to demonstrate with an example of a consistent and inconsistent system. So here's key facts. If the rank of the augmented matrix is the same as the rank of the coefficient of matrix A, then the system is consistent. For example, there is at least one solution. And if the rank are different, the system is inconsistent. For example, there is no solution. So let's look at an example. Consider the system A is 1, 2, 2, 4 and B is 3, 6. So the augmented matrix is 1, 2, 3, 2, 4, 6. So we're going to row reduce the augmented matrix, subtract 2 times row 1 from row 2. So 2 times 1 is 2, minus 2 that would give us 0. And 2 times 2 is 4, minus 4 that gives us also 0. And 2 times 3 is 6, minus 6 that gives us 0. So the rank of the augmented matrix is 1 and the rank of A is also 1. So since the ranks are equal, the system is consistent and has infinitely many solutions. So the rank nullity theorem, the theorem statement, the rank nullity theorem states that rank A plus nullity A is equal to n, where n is the number of columns in A. Okay, so what is nullity? So we have here the dimension of the null space or the solution to AX is equal to 0. Example, calculate the rank and nullity of a matrix. So the rank nullity theorem states that rank A plus nullity times A is equal to n, where n is the number of columns in A and rank A is the dimension of the column space, and the nullity times A, or the nullity A, is the dimension of the null space, so the set of solutions to X is equal to 0. So for example, if the rank of a matrix is 2 and the matrix has 3 columns, then the nullity must be nullity A is equal to 3 minus 2 is equal to 1. So this tells us that there is one free variable in the solution to the homogeneous system A is equal to 0. So in conclusion, we've learned that the rank of a matrix is an important measure of its structure. So it tells us about linear independence of the rows and columns, and it's directly connected to the solvability of linear systems. So we also learned how to compute the rank using row reduction and explore the rank nullity theorem, which connects the rank of a matrix with the dimension of its null space. Great work for today. Bye for now.